Hello, and welcome to Paleozoic PCs, the stupidest retro computer channel on YouTube. And we're back talking about the Lo-Fi video project. Been busy since the last time. As you can see, I have a whole new circuit board all put together with 6 breadboards instead of just 2. And the reason for that is remember, the whole goal for this thing, because the goalposts keep moving, had become building a complete computer out of it, not just a video card. So what we have now is this portion, which is pretty much the same as the video processor and control gals as before, and then this section right here is all new. So let's go ahead and talk about what we've actually done here, and then I will walk you through the actual hardware demo a little more. So let's go. So I put together a little presentation here. With the help of our good professor, Professor Pterosaur. So let's go ahead and talk about video display character generation. So what are raster graphics? Raster graphics describes the video hardware that we have used pretty much since like the 1970s as the primary form of computer displays. And what raster graphics refers to is graphics which are formed from pixels, which are arranged in some kind of grid and scanned onto the display according to some algorithm. This is in contrast to, say, vector graphics, where you have some sort of hardware that has like a steerable beam or a pen or something that draws continuous lines. So back in the old days, we actually did have a technology that allowed steerable beams. It was called CRTs. And the way you would draw raster graphics on a CRT is the CRT has it's got an electron beam shooting out of the front, and it makes a spot on the front of the CRT. It's focused by magnets. So you set up hardware that scans back and forth, and as it scans back and forth, you can turn the electron beam on or off, or vary its intensity. And when you have it on, you get a pixel. Where you don't, you get no pixels. And so you scan from top to bottom, then you pop back up to the top, scan it again, Bob's your uncle. So, of course, we don't use CRTs today, but we still basically do video the same way. I mean, flat panels, they aren't just a blank slate the way that a CRT is. Flat panels actually have pixels built into them. You can think of it as a grid of little light valves or light bulbs that can be turned on and off. But you still have the concept of video is sent to the display in the form of like a serial data stream, which usually updates the little lights in the display by starting at the upper right and scanning back and forth. So the reason raster displays have conquered the universe is simply because they're easy to realize. There's a lot of moving parts, so to speak, in a modern LCD display, in the sense you got literally millions of little dots, but it's simple. It's just the same unit repeated over and over again. Compared to, say, vector technology, where again, you need the ability to have something you can steer around, and you need to be able to do that fast enough that you could actually, make a picture that will, look, I'm drawing a circle. That through persistence of vision, the brain would perceive as stable. And of course, if you had many objects, then you'd have to eventually you would reach the point where describing that screen would require more data than simply, digitizing it at some level. But it is one of the drawbacks of raster graphics, is it requires a large amount of bandwidth, because you've got this thing rocking across the screen, updating pixels. If you want those pixels to update fast enough that it looks like continuous motion, or in the case of a CRT, those pixels will rapidly fade to look like a stable picture, you will have to be shoving literally millions of dots through a serial channel at the display per second to make it work. So how did a computer from the 1970s, where you might only have a few K of memory, be able to pull that off? So, like I was saying, a picture is worth 1,000 words, and that is literally true with raster graphics. A modern display, let's say your 1080p monitor, that each dot on the display requires about 4K of memory, and that's not including if you've got like 3D support or anything where you might have multiple layers. Just a 32-bit bitmap that size requires about 8 megabytes of memory. Now, obviously, the old-fashioned displays that we had back in the 70s and 80s used a lot less memory, but it was still a lot for the time. I mean, as say here, say you have like a 320 by 200 pixel display, which would be typical for like a 40 column screen. Each letter is going to be will usually be between 6 and 8 dots wide, which will be generally a byte. And then it's going to be usually at least 7 or 8 dots tall, generally 8, because you'll have like 7 lines in the character, and then there'll be a blank line in between. This means that if you are having to draw the pictures into a bitmap display, you'll have, in 40 by 25, you have 1,000 characters. And if it's black and white, you'll have 8 pixels on and off on each row, and then times 8 rows. So that's at least 8K of memory just to make a 40 column screen of text. So how did you make that work when, like the original Commodore PET or TRS-80, they came with only 4K of memory? So did they have 8K of video memory? Did they have twice as much video memory as system memory? No, those machines would have like 1K of video memory. So how did they manage to make 1K shove 8K of dots onto the screen? So they used what was called character mode graphics. So in character mode, you add a layer of indirection between the frame buffer, well, character buffer, and the screen. So instead of having to draw every dot, you simply shove a single character out into the screen and into the screen memory, and then let hardware turn that into the actual character. So let's go back to that 40 by 25 display. You'd only need 1K of memory to store 1,000 ASCII codes. So then what you do is you put a ROM, which is an example character ROM, which has the patterns to turn the that letter into that 1 byte into the 8 bytes of character rows. And in this case, this would be like, this is 128 characters here. You usually have 256 characters in a byte, so that would be like 2K of ROM plus 1K of RAM gives you a complete display instead of requiring that 8K of RAM. So this is the schematic of an actual 70s machine. This is the schematic of a 1970s Commodore PET. So, in this case, you've got 1K of video memory right here, and this is connected to the CPU via this bus that runs off to one side, and it's connected to to an address bus, which is both connected to the CPU, and it is also connected to what's called an address generator unit, which I talked about in the last few videos about how address generation is a series of counters that, as you're running through the display, it instructs the memory that you want to display what address you're at, and it triggers it to output the byte. So you see the data bus is connected to both the CPU, so when the CPU has it, and then in this case it's connected to a latch, because this memory was barely fast enough to do what was being asked of it. So the latch is here, so the output from the RAM is latched in there, so the computer can, so the video hardware can give the RAM back to the CPU as fast as possible, and then the data byte that's latched in here is then output through that character ROM we talked about, and that turns, so there's, in this case, 7 lines of the output data act as 7 address lines on the character ROM. In this case, the 8th address line is actually used to invert it, so you effectively get 256 characters out of only 128 characters worth of ROM. Now there are also 3 additional address lines, which are the, if we looked at back here, those are the row addresses. So as the address generation hardware runs through memory, it's going to paint 25 lines of characters. For each line of characters, it's going to run through. It's going to count from 0 to 7 and put that value here. So this address value, which is set once per line, is combined with this, which is the value of that one character out of 40 across, and then that value is output to the shift register, which then turns it into the serial data, which is sent to the display. So this is an actual example of how this is done. So I'm asking this question here because, again, the reason most 70s and 80s computers had character mode was because simply you couldn't really afford enough memory to just do bitmap mode. So why not just have bitmap mode now, since I'm building a computer today? Well, that's true. If I was just building this completely from scratch, I could just do a frame buffer based video system and not worry about it. But I am using an 8-bit CPU, and so there are circumstances where you only have 64K of addressable memory at once. So it can still be useful to be able to run the display by just putting one character into a spot instead of having to draw 8. And it also takes more time to draw 8 rows of dots instead of one character. So it's still useful, and more importantly, all vintage computers have it, and if we want to make a computer that is to any degree at all compatible with a real old computer, you probably need it. And it also simplifies, if you want to make like a ROM monitor or something, it means you have to have less software that works. You just can poke letters into a character buffer and they show up on the screen. You don't have to have an extensive routine that draws something. So, and the last one is when you move a little beyond the 1970s into the early 80s, a lot of early computers would also use, and even in the 70s, computers would use characters as video games sprites, essentially. It's not a real sprite. You're constrained to the grid on the screen, but there's still many games that you can do by simply moving characters around. And one of the useful features that started showing up in computers was the ability to actually redefine what the character glyphs you were displaying look like. So if you advance from beyond the PET to, say, the Commodore VIC-20, then that machine's entire graphics system was designed around the idea of programmable character sets. You could even fake having bitmap graphics by just filling the screen with a series of characters and then changing their character definitions. So it would be kind of cool if we could do that. So anyway, this is my first hardware prototype that I've shown in the previous videos. As you see, it has the CPU, which we're calling the CRTC because it does what a CRTC does. It acts as an address counter, and it also generates like sync and stuff for the display, but we're not worried about that. So when we're displaying something on the screen, basically these address lines are incremented. They're sent to the memory, and then there's this clock divider chip up here that takes the 12 megahertz clock that's generated by the CPU, and it divides it into several pixel clocks. This is what allows us to have different video modes. And then there's some control lines that run from here to here. And when we're in an active line, one of these lines basically says, okay, start outputting pixels. And it's this device that, on the correct cadence, which is set by the CPU, once per character cell meaning 8 bits of pixels, it sends the necessary read to the ROM, which this is counting up synchronously with that. So it'll fetch whatever byte of memory is being pointed to at the time. It'll throw it out here, and then this will shift it out to the monitor. That, as you see, that all fit in 5 chips essentially. You've got the CPU here, well, the MCU. These blue lines, mostly blue lines, these are the address bus, which is out on these. There's basically 2 contiguous 8-bit ports that are defined on the MCU, and they are the address lines A0 to A15. They run to this chip, and then these green lines coming out of the ROM go into the shift register. That's the data output. So, how do we turn this into a full video card for a computer? So, first off, obviously it only supports outputting pixels stored in the ROM. There's no RAM, and there's no mechanism for sharing the bus. So if it was RAM, to allow another device to access it. So basically, if we go back to the previous picture, we've got a one-way address bus that goes from this, which is essentially the bus master, to the ROM. Well, the output ports on this chip, they're active all the time. So they're always driving the address lines of the ROM. So in order to allow it to share with a computer, we'll have to be able to put a buffer of something in there that we can shut it up. It's called tri-state, where you put the output pins into a high impedance mode so they don't load the bus in any way. Um, that's what you need when you have basically anything that's driving the address bus you can call a bus master. When you have multiple bus masters that want to share devices, you need to arbitrate between them. So we have to add some external glue. I mean, hypothetically, we could, if we had a much faster MCU, we could play tricks like changing those ports from an input to an output, but we can't do that. This machine is not fast enough. But anyway, so first off, we're only connected to ROM, and we can't share that bus, so we can't really put RAM on it at all. Secondly, is the memory output goes straight to the shift register. So that's, if we were just doing graphical screens, that would be fine. But this does mean we don't have a character mode. And their third one is there's no row address lines. So on a real CRTC chip, or with like a discrete, if you were doing like discrete hardware, there would be some additional address lines so you could, you know, to tell a character ROM what row you're on. I'm almost out. I'm going to need some more control lines. We don't have enough discrete control lines to use additional lines on the CPU for the control lines. So it's not a huge problem. Next slide we'll talk about how we could deal with it, but it's a thing. So how do we solve these problems? So here is the first concept I had for moving on from the original prototype. This is what I had in mind when I sat down and started doing the new board. So you've got the same CRTC setup, got the same glue logic here, got the same shift register over here, except in this case, now we've added, first off, we've added a latch right here. Now a latch is a simple electronic device that basically you have like 8 lines going into it on one side, and you have 8 lines coming out at the other side. And when it's not latched, if there's a change on this side, it goes straight through to the other side. But then if you know, so here and here, but then if you latch it, then whatever value was on the input lines when the latch was triggered, that'll be stored in some flip-flops inside of it, and that will stay. It's basically a 1 byte memory that'll stay in there until you release the latch and do it again. Now the other thing, so I'll get to that. So what the plan was, we could simply hang this latch off of one of the same ports that drives the address bus, and simply at the start of a line we could latch the character row by using the same output pins. We just need 1 pin to control the latch, and that would be how we get our ROM address line, and that would work just fine. It even gives you, because you only need, say, 3 or 4 row address lines, you could then use the rest of them to say, you know, our character ROM, it's a 128K flash chip, so you could have multiple character sets in there and be able to switch between them by doing that. So we were simply going to throw a latch in there to drive the ROM address lines. Then we were going to put a buffer in front of each one of these. I went with a 245, even though it's strictly a little bit more than we need, simply because I had them around and they have a convenient pin layout. But the deal with the buffer is it simply takes what's on one side and it shoves it through to the other. But it also has, it's not shown on here, there's an output gate that you can instruct it. You know, it's got an output enable. See, this is mentioned over here. So on command, you can switch between what's over here coming out this side, or it going to that tri-state mode where it no longer drives a bus. So we could simply just add a tri-state buffer externally, and then we would connect those to the RAM address bus, which is connected down here to the CPU. And then when it's the video display's turn, which would be this chip is set up to timeshare between the CPU and the video hardware. When it's set up to time, when it's this video hardware's turn, it would open these buffers. That would put the address of the character buffer onto the RAM chip, and then the output would come out of the data bus on this side, and the ROM chip would be hanging there. So these would be the address lines of the ROM are connected to the data bus, and then they are combined with the contents of this latch, and then that produces the data byte, which then goes into the shift register. So basically we're just inserting this little thing so we can share, and turning the ROM from the prototype into a RAM. As I said in my bullet points when I neglected to click through, this essentially duplicates what the PET schematic was doing. You've got, except in this case there's no latch. We're just going straight through, and the reason is because this should be fast enough, these devices, for at least a reasonable CPU speed. So, pros and cons. It's historically accurate. This is how they would generally work. You'd have some RAM that was shared with the CPU, and you had a character generator ROM that was dedicated only to displaying the character graphics. It's simple. You only need the reads. You only need to have a read cycle access to the memory once per 8 pixels. The timing is simple. As long as you're willing to hold the video address on it long enough so it propagates all the way through, like I said, then there's no other coordination that really has to happen. You just flip it over, hold it, and long enough that you go for the access time of the RAM plus the ROM, then you latch it onto the shift register. As long as that doesn't take more than 8 pixel clocks, it'll work. If you really need it to go faster, well, remember, we're trying to share with the CPU, so ideally you wouldn't take more than, say, half of 8 pixel clocks, so you can give the rest to the to the CPU. But, worst case, we could throw a latch in there, but we don't need it. This would probably work at, it's 55 nanoseconds plus 70 nanoseconds for the RAM and the ROM thrown together, so that's 125 nanoseconds. That might work as fast as 4 megahertz. It'd be a little tight, but it might work. So, the con. The character generator ROM is dedicated completely to this task. It's not a big deal. That's how it was done back in the day. But, is what it is. The CPU, of course, whatever CPU we throw in there, we're going to want it to have its own. It's going to need some ROM code to boot up. So we'll have to have 2 ROM chips on the board. And the con is you are stuck with whatever character sets you stick in the ROM that's connected up there. Again, not a big deal. That was how it was with most early video cards. It just means if you want to do graphics, you have to switch to graphics mode. Now, I didn't put this on any of the diagrams, but switching to graphics mode, you could do that several ways. You could do some sort of bypass around the ROM and just feed the RAM contents directly into the shift register. The cheat I came up with was simply you could just put a pattern in the ROM, which is, the content that's come out of here is going to be a number from 0 to 255. You could just have a section of the ROM, which you would select by the latch, where 0 from 255 comes in this side, and 0 to 255 comes out the other side. Just let it go through the ROM. That would be wasteful back in the day, but of course, these days, memory's cheap, so we don't mind throwing away that. So, can we do better than that? So, our first target is a 6502 CPU. So we've talked about in a previous video how I've already set up what I will hope work clock generation on the video device, so it could share according to the same method that was used by real 70s and 80s computers like the Apple II and the Commodore 64 and such. That'd be able to share the same memory between the CPU and video without having any sort of contention by using opposite sides of the 6502's phi clock. So a light bulb went on in my head that, well, if we're using the phi clock sharing like that anyway, is there any reason, and we're doing that with RAM, is there really any reason we can't do it with ROM too? Or could we have the option of being able on the fly to instruct the video address hardware to, instead of pointing to ROM for the character set, point to a block of RAM that we set up, so suddenly we're able to do user-defined characters out of RAM, just like, again, a good example would be, say, the VIC-20 or the Commodore 64 also had redefined character sets. So, as I mentioned earlier, one method that probably someone would use if they were using a faster microcontroller would, or you could program this into an FPGA, would be to, when you got the first address, you could take the byte of memory that comes out, you could read it into the MCU, and then you could add it to some offset, and then run a second cycle by putting, on those address lines that we've already got buffered, and just run a second cycle and have that one go straight to the shift register. The thing is, this MCU is too slow to do that. It runs semi-asynchronously to the pixel clock. It changes modes. It and the MCU are going to be running at different speeds, and one of them is actually like a 1.5. The 8 megahertz clock that we're using for 40 column video is 1.5 times the CPU's clock, or it's a 1.5 division. So it'd be very awkward to try to make this work. You have very few instructions to change the direction of a port and try to catch the read at the right time. So that did not seem to be an option. But and it's also not really in this case, you'd probably have to directly clock everything with the CPU. And my goal has been not to do that. The goal has been to build this in such a way that if you really don't want to use the microcontroller, you could rip it out and put a CRTC in there. So, but we are already doing fancy stuff with that GAL, the state machine that's doing all the clocking and stuff. So, thought occurred to me, could we simply tack a tiny little bit of additional hardware on there and make it happen? So, here's the idea that occurred to me. It's basically the same setup as before. We added the buffers so we can share the address bus. We have that latch. That's the character address latch. But we've instead just pumped it again onto the same address bus. And then we've added another latch. And this latch is where the magic happens. So in this case, when we want to display a letter on the character, we've got the master timing set up. Most of the magic lives in this chip over here. So on the first tick, where there's 8 ticks for the pixel clock coming down here, and we are splitting it 50-50 between the CPU and the CRTC. So effectively, say if we're running at the 8 megahertz pixel clock, we're going to run the CPU at 4 megahertz, and the video system gets it the rest of the time. So when it's the way I've set this up is when it's the video system's turn the first time, it does the needful. The latches get opened here, or the buffer gets turned on, an address goes out. That address can be either RAM or ROM. That's controlled by the memory decoding. And then a byte is output. That byte feeds back around and goes into this latch. Then, on the next opportunity that the video hardware has to control the memory, these two chips have their output enable turned on. They put a 16-bit address onto the bus, and during that one, the memory contents goes from here into the shift register and is then clocked out to the monitor. So, effectively for every byte that gets thrown out to the monitor, there are 2 reads of memory instead of 1. Instead of, essentially, before you had 1 read of memory and then it was filtered through the ROM. But because it's separate, we no longer need to add the address times of these 2 chips together. We have, let's say we're reading from RAM for our frame buffer. The RAM I'm using is like 55 nanoseconds, so that would be good almost up to 10 megahertz. The ROM is 70 nanoseconds. That is good up to at least 6 megahertz or so. 6 megahertz would give you like an 83 nanosecond access time. So because that comes in 2 separate reads, 2 separate transactions, we can run the CPU as fast as 6 megahertz easily. So here's what we've actually built. So if we look at the computer, we've got the video timing gal right here, a master clock divider, that's where the pixel clocks are derived, the CPU, the MCU, the CRTC. I'm calling it the System Management Controller because that's the fancy name Intel came up for in the 80s for a little brain-dead CPU that would take care of things like power management and stuff that lived on the board with the main CPU. Here's the shift register that sends pixel data to the monitor. These 2 are the latches, as mentioned. This is that character latch, which we latch from the CPU at the beginning of a line. And this is these yellow wires that come around. Those are the data lines, which come off of, there's essentially a data and address bus and all this pile of grossness. See, that comes around. And then address lines come back out. So that's the phase 2 address generation, which is those 2 devices. These 2 are the buffers, which take the value, and that's for most of the line. This is the part that's incremented once per character byte. This is the thing that gates the counters that's running on this most of the time. So that's phase 1 address right here. We have both the ROM and the RAM, and they're essentially wired completely in parallel. We have a memory decode gal down here, which this sources off of like the system clock and looks at the high address lines and figures out which of these should be answering a request. And here is our CPU. We actually have a 6502 CPU wired up. This is the modern, still manufactured Western Design Center 6502 version that older CPUs would have required, the same buffer arrangements to tri-state the 6502, so it wouldn't be the bus master all of the time. The modern version of the CPU has built into it, there's an there's a line on it that when it's triggered, it puts it into the tri-state mode. and that can just be connected directly to the clock. So we don't, if this was an old 6502, we would need another set of this stuff. Without it, we don't need it. So does it work? Yes. So far in testing, it works. It seems to work up to the 6 megahertz CPU or 12 megahertz pixel clock I mentioned. And the 6502 is actually capable of running code now. The parts are a little less than a separate ROM chip. I mean, these ROM chips are very cheap. These flash chips, they're only like $1.50 each, but a latch is still cheaper. Anyway, yeah. So let's go ahead and take another closer look at the hardware. All right. So here's the board, just like we have it on the pictures. And go ahead and fire it up and take a look at what we got. So the demo loop I've got in there now, it starts out with several plates. That first one was 320 by 200. This one is 512 by 200. This is the highest graphics mode. As you see, we now support a Commodore style PET character. Now, if you look at this scroll, this is actual character mode. You can see as the characters move along, you'll see that the character that rolls off here rolls up here. So these are actual text modes. These are not static graphics anymore. And I've got it programmed for both TRS-80 and Commodore fonts. It could basically do just about anything you want. So there's that old bouncing demo, which again, this is still running off of the ROM. Now, see this red light right here? That red light just went off. When that red light goes off, the CPU is running. So there's a reset line which is controlled by the MCU right here. And when the CPU is held in reset during all those earlier demos, and that reset line is also connected to the memory mapper chip right here. So when reset is held high, all of memory, the ROM chip is the only thing that gets selected. So there's room for those pictures. Now in this mode, this actually switches to a memory map in which there's 44K of RAM at the bottom of the memory map. And then there is font ROM is at the 44K mark, which is very similar. I think that's where a VIC-20 keeps it. Or Commodore 64, I don't remember. And then above that is ROM code. Now, what is running here is actually running on the CPU, on the 6502. This is some diagnostic code I wrote 8 years ago when I was attempting to fix a Commodore PET. It's called PET Tester. And now you see the red light came back on. So now we've run back through to the beginning of the demo again. So the 6502 again is it's running completely independently once it's triggered, essentially, from anything that the CPU does other than the CPU is generating the clock. It's not generating the clock with software. It's simply these things have a fuse setting that allows the clock that they generate with their crystal to come out. I don't even need to do that. I could use an external clock and just feed it to both devices, but this is a way to get it for free. So basically all the magic is the clock that's derived here is fed into this, and this has the entire state machine. I talked about the state machine in my last video about GALs if you want to go back and talk about that. The only addition is I've added additional lines which control these buffers. So this is running at 4 megahertz. The original PET ran at 1 megahertz. If I move this wire, it's actually a turbo switch. And with the turbo switch set or unset, it runs at the same speed as an original PET. So it's going to run this for a little while. And now, without resetting the CPU, we just changed video modes. So we're running at the higher pixel clock. We're running at 6, which means this is running a little faster. With the turbo switch unset, this is running at 1.5 megahertz instead of 1 megahertz as before. And now this is the 6 megahertz clock, which means the CPU is now running at 1/8 of, it's like running at 0.75 megahertz. Now, if I grab this and put it back, now this needs to be debounced before it's going to be reliable, because it just directly changes it. So occasionally I crash it if I try switching the turbo switch. You can see it sped up a lot. So now it's running at 3 megahertz instead of 1.5. Oh, sorry, 0.75. So, yeah. So one thing is, remember the indirection. So when we're running in character mode, we're pointing at memory where we have the font. We have the font stored in memory, and the data byte comes out of RAM or ROM, because in this case this is just text stored in the ROM that it's actually hitting the ROM twice. It reads the byte and feeds it back around and then gets the ROM. It gets the character glyph. When it's doing the pictures, there's simply one spot in ROM where I mentioned that we could just simply put the numbers 0 through 255 in a row. That's what it's hitting. I mean, in theory, you could do some special effects where, like, if you wanted to do dissolves or something, you could go and you could change that translation table, and it would like fade or reverse the text. So here we go. We're running at 4 megahertz. I'll see if I can find a video of the old PET tester ROM running, and we can put them side by side. You'll see how much faster it's running. But as you see, this is 4 megahertz. And you'll see when we switch to the higher dot clock, to the 64 column mode, we will see that it actually runs even faster. So get a rhythm here, even faster. So there we go. It's a computer now. So I think future installments will concentrate on the computer. So as you have seen on the demo reel, I've decided to call this the Dino 128. It's going to be, the goal here is to make a machine that starts off as compatible with a Commodore PET, or at least loosely compatible with a Commodore PET, and then we try to evolve this. Obviously, it supports bitmap graphics, it supports redefinable character sets. So yeah, the next step, I think, is going to be we're going to in the next video I might talk about, I'm going to see if I can actually get it to fire up with the Commodore Basic Interpreter. I just need to write that into the flash in place of the PET tester ROM. And then I don't know if it will get all the way to the basic. It's been too long since I was messing with the Commodore PETs. I don't remember if it's going to make it all the way to the basic prompt without having the I/O in place. So it may just get to the ready prompt and freeze, or it may drop to the debugger. But the next step, obviously, will be to start trying to put some I/O to it, so we can actually hook up a keyboard or something and see what we got. So there we go. I guess the next video won't be the DIY lo-fi video project anymore. It will be the Dino 128 project. So thank you very much for watching. Have a good night.